Hello, in this session I will be discussing the analysis of variance or the Anova technique with the help of MS Excel package. In statistics, we generally encounter with the practical problems and we do them with the help of our hands and calculator. But sometimes I feel it is necessary to check and verify our results with the help of the computers software which are provided to us, and I would like to say that in this series most of my videos will be based on these things. So today, in using the MS Excel software for checking the analysis of variance for a one-way data. Now for a one-way ANOVA, the variation for the experimental units is generally achieved in terms of a single factor. The variation is generally caused by a single factor. For example, here we have taken this problem and we want to, here we are given that the following table shows the lives in hours of 4 batches of electric lamps. So here we are given, so we can see that the experimental units is the life of bulbs. We want to check their life hours, and the bulbs, the variation between the bulbs is caused by the batches. They are producing different batches in the factory, so the batches are the variation factors. So we are going to perform an analysis of variance and show that a significant stress does not reject their homogeneity. That is, we cannot say that they differ in batches. There is no difference in with respect to the batches. So now the data is from the question. We have written down it in Excel. So my null hypothesis is that the bulbs in all the batches are homogeneous in life hours against the alternative, that is the bulbs in all the batches differ in life hours. So now the data here is to be entered in a particular way because Excel cannot read any haphazard type of data. The data has to be entered in a systematic manner so that Excel can read it and consider it for testing the analysis of variance. So now these are the life hours of the bulbs. Now to conduct the ANOVA, we select, we go to the data, and the data analysis package is provided. Now here we can see that the variation is achieved with the help of, due to the only one factor, that is the batches of the bulbs. So here we are going to use ANOVA single factor. So now our input range is this. Yes, the data is grouped by columns. You can see it's column wise. Yes, there are labels in the first row. The level of significance, the alpha means the level of significance is 0.05, and the output range is this. This is our output range, and so okay, here we go. So now we have been provided here with the ANOVA. Now our interest lies in this one, in this thing. There's the analysis of variance table, the ANOVA table, which we call it popularly. Now see, here the variation is achieved only between groups, that is between batches. Here the groups in this summary table A, B, C, D, they are the batches, different batches. Count is the number of bulbs in each batch. These are all mathematical things. Sum of all, average, and the variance are very easy to compute. Not that much of interest, but the main thing is that the ANOVA table is the main thing here. So the source of variation, as I had said earlier, it's between groups, in between batches. Within groups is the inherent error, which is a part of any experiment. Then I said the sum of squares. These are the sum of squares between groups, sum of squares within groups. That's the total sum of squares. These are the derivatives of freedom. So here we have 4 groups, but it's 4 minus 1, 3. And within groups, it is computed with the yellow total. Total we have 26 bulbs, but 1 DF is less because in Anova there is an assumption. I'll be saying it on later in theoretical video. Today I'm going to only show the practical aspect. So just keep it in mind, if we have total n number of observations, the total DF will be n minus 1, and if there are k groups, then there will be k minus 1. So the within groups becomes that a total minus the between group, that is n minus 1 minus k, and it becomes plus 1, that is n minus k. So here 25 minus 3 becomes 22. The ms is the mean sum of squares, which is obtained by dividing the sum of squares by the df's. The f is the f ratio, that is ms between groups by ms within groups, and which is obtained, this is the f observed value of the f ratio, which is 2.149. P value, the probability value, I will be coming to it later on. The f critical, it is obtained from the table, the statistical tables. It is f critical is that f 0.05 at level of significance 0.0, that is at 5% level of significance, with df 3 and 22. So here we see that the f observed is less than the f critical. Now when the f observed is more than the f critical, we reject h naught at that level of significance. That is, here we reject h naught, that here we failed to reject the h naught at 5% level of significance, because the f observed is less than the f critical value. Now in terms of the probability value, we see we actually reject the probability value if it is less than the level of significance, but here the p value is 0.12, which is more than 0.05, so we fail to reject the null. I repeat, we fail to reject the null here, and so we conclude that as the observed f is less than the f crit, we fail to reject the null and conclude that the life hours of the bulbs do not differ with respect to the batches. That is, there is no variation due to batches. The life hours of the bulbs do not differ with respect to the batches. That's it from this video. I hope you enjoyed. Please subscribe this channel and stay tuned for more. I will be covering the Anova in this week. Later on I will be going to any other topic. Mainly I am interested in the practical aspects, but I will surely go to the theoretical aspects as well. Thank you.